Hi, Professor. I'm Sharat Kumar Kaparti. We are from Group 4. We are a team of 5 people. They are me, Hemant, Praneeth, Radha, and Hannah. Now we are going to explain how we have implemented the breadth first search algorithm, depth first search algorithm, and an A star algorithm traversing the nodes. Firstly, if we look at the given route map, it represents an undirected graph. Now, what does it mean? What does an undirected graph means? It is a set of nodes or points which are connected together where all the edges are bidirectional. That is, each of the nodes is connected to any of the other node. And traversal means to visit all the nodes or points in some systematic order. With the given route maps, from the figure, we have transferred through the nodes in a given two cases from one city to the another city by using breadth first search algorithm and depth first search algorithm. And for A star algorithm, we have used the straight line distance heuristic method with Python to traverse through the node points or the cities in the given same two cases. Coming to the mechanism we have used in these three methods are, for the depth first search algorithm, we have used the LIFO, which means last in, first out. For breadth first search algorithm, we have used the FIFO, which means first in, first out. For A star algorithm, we have used for f of n equal to g of n plus h of n. These all the steps are clearly explained and executed by my other team members. By the end of the report, we will conclude which search method would be better for us. Thank you.
Hello, my name is Hannah, and in this video presentation I'm going to show you how our team implemented three different graph search algorithms such as DFS, BFS, and A star search in the context of finding a path from one city to another on the Romanian map. Let's start with the problem definition. We've been given an undirected graph where nodes represent cities and edges represents roads between these cities. Since graph is undirected, you can go from one node to another back and forth. Our goal is to find path between one city to another, technically speaking from one node to another. Okay, let's first review how all these search algorithms work by looking at this pseudocode. At the beginning, we initialize our state of problem, in our case, add starting city to a frontier list. Then, in the loop, we do the next actions. First, we check that we have elements in our frontier list. If no, we exit with the failure state, which means we couldn't find a path. Then, depending on the algorithm, we pick one node from the queue to expand. In case of DFS, we use last in first out queue as a list, which means we take the last added element from the queue and expand a deepest node first. In case of BFS, we use first in, first out queue as a list, which means we take the first element from the queue and expand shallowest node first. And in case of A star search, we need to find a node with the best F value, which is the sum of path cost to this node plus heuristic value. Then, before expanding this node, we check whether this node represents our goal state, stopping node. If yes, then we return a solution. Otherwise, we expand the node by adding its neighbors to the frontier list. So, here we see that there are only three major differences between these algorithms. First, which leaf node to expand next. Second, whether to check for visited nodes or not. And third, which data structure use for the frontier to expand nodes. So, In the DFS implementation, we have our main function that calls DFS, where we pass our graph within starting node. For example, here is Bucharest, and stopping node, this is Arad. So let's see how our algorithm works. And as we can see, DFS found a path from Bucharest to Arad with a total cost of 575. So DFS function starts with the initialization of the visited nodes list. We will store all visited nodes. Then we create our initial state. In addition to name of starting node, we also store two other helpful parameters, path and path cost. Path will store the full path to these nodes from the starting point, and path cost is not used by the algorithm directly, but we're still calculating cost for the path for our analysis. Then we loop through nodes in this queue. In the loop first, we need to choose the leaf for expansion. Since this is a DFS, we take last added node first. We print path for this node. Then here we check whether this node is our stopping point. If yes, we just print this path and exit. But if not, we verified that we didn't visit this node before to avoid infinite loop, and if not, we start expanding this node. We get all node neighbors by its name, iterate over them, and building a new object that represent a path to this node with total cost value, and adding this for a frontier queue. If we reach the end of our function, then we couldn't find a path between two nodes, we are printing an error. Let's see the output, for example, for our second situation. As we can see, this is the total cost, and yeah, DFS found the path from Lugoj to Bucharest with total cost of 804. This is the long one. So let's switch to the BFS and see what output will be here. Here, implementation is almost identical, except for the part where we use first in, first out queue to expand shallowest nodes first. Let's see, we have, okay, Lugoj, Bucharest. For this program, BFS. So this path is shorter than from DFS, Lugoji, Mihandia, Drobeta, Craiova, Petresti, and Bucharest, and cost of this path is 504. We can try the second case and run the program again. Bucharest, Făgăraș, Sibiu, and Arad. Found path for the second case. And now, time to my favorite algorithm, it's A* search. Here, yep. Implementation is similar, but now we're expanding a node with the lowest F cost. To simplify this process, I create a special method called nextNode, which returns a leaf node for expansion. it finds index of the node and remove this from the queue. We iterates over all nodes in our frontier list and calculates the sum of current costs to this path plus heuristic value. Let's see output for a star search. As we can see, this is the shortest path, which cost only 504. And for the second case, I need to switch start point. Oops. And stopping point. And path from Arad to Bucharest cost only 418. This is the shortest path. So I think we can see that A-star algorithm was able to find the best, shortest path from one city to another. All right, that was all I wanted to share, and thank you for your time. Bye.
Hi, hello everyone. My name is Hemant and I am from Group 4 in Advanced Artificial Intelligence. Today I am here to explain about depth first search algorithm. Before going to that, what is AI? Artificial intelligence. Artificial intelligence is a man-made code where the agents will help to run the code and improvises day by day. In this artificial intelligence, there are few search algorithms which are divided into two different parts. One is uninformed and another one is informed. In uninformed, we can get uh, depth first search, breadth first search, and uniform cost search. Wherein informed search, we get greedy search, A-star search, and graphs. So today my topic is depth first search algorithm, which is in uniform uninformed direction. So what is uninformed direction? So in uninformed direction, there will be to and fro movement. So it can go backward and forward. So before depth first search is mainly depends upon LIFO, last in first out mechanism. So it means it goes on dividing the nodes from one point from the parent node, and after that it goes on expanding till it reaches to endpoint. It goes deep into nodes and search each and every and backgrounds it everything. So I want to show before that I want to explain our map. Here is our map. So our target, according to our problem statement, there are two problems. One is from we have to find DFS from means depth first search from Bucharest to Arad, and another from is Lugoj to Bucharest. So these are two our problems. So before go, yeah, as I said here, you can see it goes like tree and backtracking everything. It goes deep and deep. It main mechanism is for it means last in first out. So here is the code where our friend Hannah has done the code very well. Yeah, we have two codes in our group. Basically, we have two codes. One is done with me, Pranit, and Radha, and another one is Hannah. And so let me show that one. New share. Okay. Let me show the codes for you first. Yeah, you can see the codes. So this one is Hannah's code. She did it very well. Yeah. The main difference between ours and Hannah's is she made a code which memorize all the paths and how the path is going, how the search is going on. So after going through all these paths, it finally comes to the best path. So you can see Bucharest, Pitești, and everything. So it is basically from Bucharest to Aran, where in our code it's like, yeah, we have to enter. Let me run this code. So here we have to start. Uh, First of all, we have to enter our code. I mean, first node. Let me enter the first node, start node, and after that, the end is Bucharest. So when we run this, we only have in this code, we only have this one. Can you see this? Yeah, the only final path it is seeing. So that's why we gone through HANA's, and it is the best code. So we implemented this throughout our project. Thank you for HANA. And so I want to explain how the path is going, and you can clearly, I want to represent in a flow chart or visualization of DFS, you can say. So I'm showing this 1 minute. Yeah, it's from Bucharest to Aran. So you can see, yeah, Bucharest is the first one, first node, primary node. And from Bucharest, it divided into 4 nodes. One is Fagares, Urgiseni, Urigu, and Pitesi. So basically, these all spellings are tough. If I spell it wrong, sorry for that. And from Pitesi, the path is going. You can see the arrows, how the path is going on, how the search is going through all this. Some Pitesi, it's jumps to it divided into Bucharest, Craiova, and remains. Here Bucharest is already completed, so that it's blocked somewhere here, so it will not repeat it again. So it's out from this. So like that, it goes on continue like this. Same with Lugoj to Bucharest. Let me show that. Yeah. According to the map, it divides into the nodes and completes this. Yeah. From Lukoji to Mehadia, Timisoara, and basically it's from internet. I mean, I spell these are all from Romania map, something like that. Yeah. It's not to spell. Yeah, which I restrained once again. I want to see this one. Okay. Yeah. So here we done our report. This is my DFS, and thanks for our group members, Hannah, Praneeth, Sharath, and Radha for helping me through this, and thank you.
Hello everyone, I'm Radha Krishna. Now I'm going to talk about breadth first search algorithm. Alongside the depth first search algorithm, BFS is one of the fundamental search algorithms used to explore nodes and edges of a graph. The breadth first search algorithm is particularly useful for one thing, which is finding the shortest path of an uninformed graph. A breadth first search starts at some arbitrary node of graph and explores the neighbor nodes first before moving to the next level neighbors. So now, and it also uses a FIFO queue mechanism, which is first in, first out, as we all know. Now, the question here is, perform a BFS search starting at node Bucharest and stopping at node Arad. Now, here is Bucharest and here is Arad. Now, we have to write a Python program which starts at Bucharest and moves on to Arad. As I already said, breadth first search algorithm goes to the neighbors first. I know here neighbors are Gheorghiu, Pitești, Fagares, and Urgiseni. So now, here, sorry, here, Fagares, Ujasini, Guzru, Pitesti. And after that, Krakowa. Now this Pitesti expands into Craiova, Rebet and CBU. Let's see. Ujasini, Bujas,
Yeah. Hi, everyone. I'm Pranit. I'm from group number 4. Coming to the assignment, I'll explain today about the A-star algorithm. The A-star algorithm is one of the informal search, and it's the best first search algorithm because it will run through the shortest path. It will give the shortest path, whichever it is. And the entire A-star algorithm will run on this simple mechanism, that is f of n is equal to g of n plus h of n. Here the f of n is the total estimated cost of the path through n to the goal, and the h of n is, it is a heuristic function. This estimate the cost of cheapest path from n to the goal, and g of n is the cost of the cheap path. It's a cost of the path from the starting point to the node, depending on the f of n value. So whichever is the least f of n value, then it will sort out based on these three things. Yeah, coming to the code. Yeah, me, Radha, and Hemant implemented this code, and this is a basic input. This is a basic code, and after that, Hannah and Sharat implemented the advanced code. I'll tell you what is the difference between this code and that code. Okay, coming to this one, first of all, this is a A-star search. This is a main thing. We need 3 parameters. First is graph. It's a g of n value. It's a heuristic. It's a h of n value, starting and ending point. First, we give the starting node as 0 and ending node as 0. Then coming to the, we'll define the function g, function h, and function f. Here we write the f is equal to g plus h. As per the given assignment, these are the h of n heuristic values, and these are the h of n values, and these will calculate the these are h of n values. We'll calculate the g of n values based on these 2 node points. So we'll define all these h of n values here, heuristic values, and we'll define all g of n values here, depending on the entry point and exit point, entry point and stopping point. It will decide which value it has to take from this list. So, for example, if we gave the starting point as Arad and stopping point as Butcher, we'll run this code for. Okay, it shows Arab, CBU, Nisu, Itesti, Bucharest. It is the shortest point from these from this Arab node to the Bucharest node. We'll see what is happening in the backend. Okay. Here, the starting node is Arad. After Arad, it will split into, go to either Zerin, Timisoara, CPU as per the map given in the assignment. Here, Arad, it can go to Zerin, it can go to Timisoara, it can go to CPU. So, depends on the calculation. Yeah, it will take these 3 things. For when compared to these 3 things, the value of 393 f of n CPU value is least. It's a lowest value. Then it will come to the CPU. The shortest path is CPU 393. Then it will split into CPU. Here also 3 parts. When you come into a CPU, Fagras, Imnisu, and Aradia. Again, it will split into 3 parts. Here, the shortest path again is Imnisu. So it is 413. F of n calculated based on it. Okay, if we take one example, how is the g of n is calculated? Okay, here h of n for Rimini issue is 193. It is given here. Rimini issue 193. Then it will g of n is 140 plus 80. The distance from Arab to Rimini issue. So Arab to 140, Sibiu to Rimini issue 80. So 220. So it calculated based on this. This is a basic mechanism. This is a basic step. That's it. And then from Rimini issue, it again split into Pitesti and Craiova. When compared to these two, Pitesti is the least distance. Again, here f of n calculated, and the value is 450. It's cost of the path. And where g of n is 220 and h of s is 193. Again from Pitesti, it can go to Craiova, Bucharest. Pitesti, it can go to Craiova, Bucharest. But our stopping point is Bucharest, and it's finally stopped here. It's 480. F of n is it's a g of n value 317 plus 101, and h of n is 0, Bucharest, because Bucharest h of n is 0. So final the 418. So I said that in the end I'll tell what's the difference between our code and the first one code and this code. In this output, it will show the cost, but in this one it will only show the path. Yeah, but it's a basic code. Both will work. Yeah, I appreciate both Sharath and Hannah. They done very well. Thank you.
Hi Professor, we're back with the last part of the video. It's last but not the least one. It's a conclusion part. As we have discussed in the beginning of this project about the 3 such different algorithms which we have used. One of them is informed and another to be uninformed. By performing this project, we analyzed that informed such operations better than an uninformed search, since we need to traverse more edges to reach the destination vertex from the source vertex. One thing like we got to know about this is A-star algorithm is the best search algorithm amongst others, because the only con is that it's not always helpful in finding the shortest pathway, since it majorly uses the value of heuristic approximations. Thank you, Professor, and that's all for today. Thank you.